So we have seen a few methods that we can numerically approximate um, the optimum of a unidimensional function. So we saw grid search, and we saw trying to find the root of the derivative using uniroot and Newton-Raphson. And we saw we can use the built-in function optimize in R to do it. Now let's move on to multidimensional optimization. The optimization problem becomes more and more challenging when we consider functions of several variables. However, this is an extremely common problem in statistics. So a very common optimization problem in statistics is finding the parameter of a model that maximizes the likelihood function. In other words, finding the MLE. Recall that the theta hat MLE is given by the value of theta such that the likelihood function is maximized. So you can see here, the likelihood function is the objective, and we are trying to find a theta, which can be a scalar or a vector that maximizes the objective. We actually can extend the Newton-Raphson method to n dimensions. Recall that the Newton-Raphson method for one-dimensional optimization is essentially equivalent to updating the x at each step with the current x value minus the ratio of the first derivative evaluated at the current value and the second derivative of the function evaluated at the current value. This can be generalized to n dimensions. Specifically, the unidimensional f prime of xk is generalized to the gradient vector evaluated at both xk. Xk is now a vector. The gradient, denoted by this inverted triangle called nabla, is given by the vector where each entry is the partial derivative of f with respect to a dimension of x evaluated at the current xk. And the second derivative of f evaluated at xk, which is here in the denominator, is generalized to n-dimensional to the Hessian matrix evaluated at xk. So that's quite a bit of multivariate calculus review over here. Recall that the Hessian matrix, denoted by h of f evaluated at xk, is a n by n square matrix, where the ijth entry is given by the second partial derivative of the f function against the ith and the jth dimension of x, and this is evaluated at the current xk value. So with the Hessian replacing the second derivative and the gradient vector replacing the first derivative, the iterative updating formula for the multidimensional case can be generalized to the following, where the k plus 1th x is going to be equal to the kth x minus the inverse of the Hessian matrix times the gradient of f, evaluated both at the current xk. So let's see a toy example of maximizing a function and finding its gradient and Hessian and applying the Newton-Raphson multidimensional methods. Suppose we want to find the maximum of f of x, which is given by this formula over here. So you can see x in this case has two dimensions, x1 and x2. We can find the gradient, which is equal to the partial derivative of f against x1, which is the first entry, and then the second entry is the partial derivative against x2. So you can see that in this case, the gradient vector is given by this length 2 vector. And the corresponding Hessian is given by the gradient, so each entry of the gradient taking the derivative against x1 and x2 again. And in this case, we get a Hessian matrix that's 2 by 2. First entry is the first partial derivative here and taking the partial derivative again against x1. And that gives negative 6 times x1 squared plus 2x2 minus 1. And then this entry here and this entry here will be either the first entry of the gradient taking the partial derivative against x2, or the second entry taking the partial derivative against x1. And both of them we get 2x1. And then the last one will be the second entry of the gradient taking the partial derivative against x2, and that gives us negative 1. So now we have found what is the gradient and the Hessian for this function we want to maximize. Let's create functions for f, the gradient of f, and the Hessian matrix of f. These functions all take the similar form where the input is the x vector and then evaluates what the output is. So for the function, it just outputs what is f of x. For the gradient, it will return a length 2 vector where the entries are given by the formula on the last page. Similarly, for the Hessian, it's going to take value x, which is a vector, and then outputs a 2 by 2 matrix where the entries are given on the last page. Once we have the functions for the gradient and the Hessian and the original function, we'll be able to implement the Newton-Raphson algorithm to find the optimum. We will start at the initial value x0 of 5 and 5. In other words, the initial value for x1 and x2 are both 5. And this time, let's just run this for a total of 100 iterations. Here's the code for implementing the iterative Newton-Raphson steps. At the beginning, let's set, sorry, you can ignore this line. There's some code that I originally wrote and I don't think it's used anymore. So this line is not needed and this line is not needed either. Okay, so let's look at the rest of the code. Actually, let me pause here and just update the slides. Okay, so sorry for the inconvenience. I've deleted the redundant code. So now this is the code for implementing the Newton-Raphson for this example. So we begin with evaluating the f function at the current initial value x, and x is set to negative 5 and 5. And in each subsequent iteration from 1 to 100, we will first evaluate the gradient and the Hessian at the current x value. And then instead of inverting the Hessian matrix, which is actually quite computationally intensive, we will solve for x. So we will solve for h times s is equal to the gradient. You can see that the solution s is essentially h inverse times the gradient. So let's set s to be solve of h and grad. And then we will be able to update the x value by using the iterative update formula. The next x value will be updated to be the current one minus s. You can see that this is equivalent to x minus h inverse times the gradient. And let's store this x value at the current iteration into this x's matrix. Lastly, we will need to update the value of the f function. So since our x is updated, we need to evaluate f again at the current x value. So here are the results. This was iterated for a total of 100 iterations. And then the resulting solution, x, is the vector of 1 and 1. The corresponding fx, which is the optimum or the f function evaluated at the optimum that the Newton-Raphson method found, is equal to 0. If you return to this function, you can see that the maximum is exactly attained when both x1 and x2 is equal to 1. In that case, this term, which is negative, will evaluate, which is non-positive, will evaluate to 0, and so would this term. So the resulting objective is equal to 0. An alternative is to use the built-in optim function, which is a function that can be used to find the minimum. So we mentioned the built-in optimize function earlier, which is used for one-dimensional problems. The multidimensional counterpart of it is called optim. Essentially, we just need to specify the initial values and the objective function. Because in this case, the optim function finds the minimum, we will set the objective function not to be the original f function, but instead the negative of that. Finding the minimum of the negative of f will give us the maximum of f. And we can see that the resulting parameter approximation are 0.99 and 0.99, which are quite close to the solution we got using Newton-Raphson. To wrap up, we will see an example of maximum likelihood estimation of the gamma distribution shape and rate parameters. Let's suppose that x1, x2 to xn is a random sample from the gamma distribution with parameters r and lambda. In this case, we have collected data, and the parameter vector we need to estimate is theta that is equal to the vector of r and lambda. And the likelihood of theta, or of r and lambda, is given as follows. This is essentially the joint density of the observed random samples, given the particular r and lambda value. So that's equal to the product from I from 1 to n of the probability of observing a particular xi under a gamma r lambda distribution. Instead of working with the likelihood, which involves products, we will work with the log likelihood function. This is equivalent as working with the likelihood because the maximizer of the log likelihood is going to be the same as the maximizer of the original likelihood function. In other words, our MLE. The log likelihood is given by small l, which is the natural log of the original likelihood function. And by taking the log, this becomes a summation from 1 to n of the log of the original gamma density for xi. With some algebraic manipulations and simplifications, this will become n times r times log of lambda minus n times log of gamma evaluated at r plus r minus 1 times the sum of the log xi's minus lambda times the sum of the xi's. So we will try to find what value of r and lambda will maximize this function or minimize its negative. So here's a function for the negative of the log likelihood. We convert it to negative because the optim function by default finds the minimum. So by doing the negative log likelihood and finding its minimum, it's going to be the maximum of the log likelihood, which is the same as the maximum of the likelihood, or our MLE. So this is the objective we want to minimize, which is negative log likelihood. It takes input of a theta vector containing the r and lambda and the observed data vector x. And then you can see that with some algebraic manipulations, it returns us the negative of the log likelihood, where we use the formula on the last page. Now let's generate some data with a total of 100 samples from the gamma distribution with r equals 5 and lambda equals 2. And let's see whether the MLE that we find using the optim function recovers the true parameter. So here's the code for implementing this. You can see it's really short. So r is equal to 5 and lambda is equal to 2. We will use this and the r gamma function in R to generate our x's, which is a sample of size 100 with rate of 5 and a shape of 5 and rate of lambda rate of 2. And then we will use the optim function to find the minimum of the log likelihood. We specify the 1, 1 as the initial guess. And then the objective function is the LL function we just created for the negative log likelihood. And we also feed in the data vector, x equals to x, where x is the samples we got. And we can see that here are the parameter estimates that we got for this simulation study. The estimated R was 4.2, which is somewhat close to 5. This is just one replication and there's some randomness. And the corresponding lambda estimate was 1.6, which is somewhat close to the true value of 2. Let's try to conduct a Monte Carlo study with 10,000 replications. And in each replication, we'll generate the data from the gamma 5-2 distribution, a sample of size 100, and we will compute the MLE using the earlier code. And in the end, across the 10,000 replications, let's look at the approximated sampling distribution of the maximum likelihood estimator. If you have taken 410 or 510, you might have learned that the MLE is asymptotically normally distributed, where the mean is the true value of the parameter, and the standard error is given by the square root of 1 over the information matrix. So here's the code for this. M is equal to 10,000. That's the times that we are going to replicate. In each replication, so we're using the replicate function here, and in each replication, we'll generate our x's, which are random samples from gamma distribution of size 100. And then we'll use the optim function and ask it to output the parameters, so the par object here, which are our R and lambda estimates. You can see that the resulting theta hat MLE object, the result of the replications, is a matrix with 2 rows and 10,000 columns. Each column is the MLE for that particular replication. So we can look at the empirical densities of the MLEs. Here's the code for plotting the empirical density of the first row, which is the R hat MLE, and then that of the second row, which is lambda hat using MLE. And here are the resulting histograms. You can see for both of them, the mode or the center of the distribution is somewhere close to the true value. For R, this is close to the true value of 5. And for lambda, this is close to the true value of 2. And then for the rest of it, it is approximately normally distributed around the true value.